So now let's apply the idea. Now I'll show you exactly how to compute using some polynomials. We'll take 3 of them. So first we start with Legendre polynomials. Okay. So Gauss quadrature requires orthogonal polynomials. So we start with simplest of all polynomials, which is Legendre. Now, so Legendre polynomial, some of you who have done this, it comes in mathematical physics and quantum mechanics. It is comes in this equation, okay? Either 0 or some E phi. Now, these are the first six Legendre polynomials: 1x, 3x squared by 2 minus 1, and so on. Okay. So we are just worried about 1D right now. Okay. So I'll show you 2D bit later. So here I'm plotting these 6 polynomials. So first one is constant, right? So this is constant. Second one is x. So this is 1 and x. X is the yellow line. Third one is 3 is a quadratic function, which is green line. And if you go even to G3, this is the pink line. So you can plot them. I mean, in fact, in Python, we can just call polynomials. Okay, so there is a way to do it. It can easily be done. Okay, now this is defined from -1 to 1. Please keep in mind, is -1 to 1. But we can make a change of variable to get integration from any finite a to finite b. Okay, but it should be finite. Both the limits should be finite. Now, so the derivation, some of it I do it in the notes, or you can look at some reference. So here I just state the formula. Okay, so right now I'm denoting this Legendre polynomials by G. You know? So there are too many L's. We are Lagrange, and we are Ligueur right now, coming up a few slides later. So I just denote it by G. So Gij dx is the orthogonal because, well, it's a property of the polynomial. So we have delta ij, and the prefactor, which is a weight function, no, not weight function, which is a gamma. This gamma is 2 by 2j plus 1. Okay, and weight function is 1, right? There is no h of x here, so that means hx is 1. So weight function h of x equal to 1, and using the formula of Gauss quadrature, we can derive Wj. So there's some more simplification has been done, but well, this is the formula. So this is the weight, and the roots are roots of the highest polynomial. So if I n points, then I should take root of phi n. Okay, or right now gn. So we start with 2 points. We need to have at least 2 points, right? I mean, to integrate, we need 2 points. So 2 points. So that is, if you recall, G2 was 3 by 2x squared minus 1, right? That is G2x. And he set this to 0. So x will be 1 by root 3. Just see. No, I think I made a mistake. So half is outside. 3 squared by 2 minus half. So let's see what it is. Yeah, so 3x squared minus 1. Yeah, so yeah, I made it. So it is 3x squared minus 1, all of it divided by half. Okay, so this gives us a thing that x equal to 1 by root 3 and minus 1 by root 3, so plus minus. Okay, so this is what I got. Xj is plus minus root 3. Okay, these are roots of G2. And the weight we can just substitute in the formula, you'll get 1. Okay, you can test it out, it just works like that. Now with 3 points, it's a cubic equation. So the 3 roots, and weights will be different for different, it depends. Please remember Wj depends on Xj. So Wj depends on Xj. So for 0, the weight is 8 by 9. And for this plus minus 1 by root 3 by 5 is 5 by 9. Okay, so we have all these weights. Okay, now I'm showing in the next slide that we don't need to remember them. In fact, Python has a function in SciPy. We can just invoke that function and get the weights. Okay, but these are good to kind of always don't really rely on computer as a black box. The whole idea of computational physics is that we're trying to see the working of some algorithms, though some of it is now black box. Now, so here I try to do integrate x8 dx minus 1 to 1. Let me just try to get rid of this. I'm not. Okay, so this is integral I want to do, x8 dx. Okay, now of course this is an exact number. I mean, this 2 by 9, right? That's the answer. But to test your algorithm, it's best to do it with something which I have the exact results. Whether this is a very important tool. No? So even for very complex programs, we test it with something for which we know the result. Okay, so testing is done with basically with analytical results. You test your code against analytical results. Okay. Now, so from SciPy special, I get this root Legendre. Okay, so this is the module root Legendre. Okay. Now, for the standard x8 returns x8. Now, how do I get the roots? So this I just call this function root Legendre, and so this will give a list. So xi is the roots which I need. Xj I called in the previous slide, and wi is the weight. And for given Legendre of order n, so we need n. So I'm right now doing for 2 to 6, n equal to 2, n equal to 3, and so on. Okay. So I just do it for various n's, and I get xi's. Okay. Now I compute yi at given xi. So we have given xi, I compute yi. So, so once we have this, then we can get integral by just. So what is it? You remember the integral was wi yi. Okay, so we can get the integral right here. I just sum up. Okay, so you can use the sum function, which is more efficient, and that will give you the integral. And of course, we are doing for a loop, so I just print them for every n, and the answer is 2 by 9, so I just get the error. Okay, it turns out okay, so it's exact. So x8 will okay. So I should go back. So this integral will be exact for what n? So I want exact number 2 by 9. So for some n it will be exact, but not for all n. Okay, so remember that 2n minus 1 for n points I can get polynomial, which is exact integral for polynomial 2n minus 1. So if I put 5, then I get 9, which is correct. If I put 4, then I cannot get, right, because that will be good up to x power 7. So 5 is the correct answer, and so we can just print it. I didn't write it here, but we'll get errors for n equal to 2. There'll definitely be error, but with x equal to 5, answer is exact. Okay. Now we can do the integral for exponential. Now this will not be exact, right, for n equal to 5, 6, because it's an infinite order polynomial. And it turns out with n equal to 5, the error is 10 power minus 13, which is good accuracy. I mean, for practical purpose, this is very good. So we can estimate, of course, by remember the formula. It was 2n minus derivative 2n minus 1 h to the power 2n, I think. Yeah, okay. So so these are pretty accurate. I mean, this method is very accurate. Now let's take another example, which is slightly more complicated. Or other polynomial, other polynomial, Ligard polynomial. Okay. So Ligard polynomial is used for integrating 0 to infinity. Okay. So one limit is infinity, other limit is 0. Okay. So I just here write down 4 of these polynomials, leading order polynomials, x minus x plus 1, this and this. Okay, so 4 of them. Now you can plot them. These functions, of course, grow quite rapidly with x. So you can see that for like this one, this is 0 and 1. Okay, so one is not looking like a straight line. Why? Because I put a semi-log scale. Why? This is in semi-log scale, right? Everybody knows what is semi-log scale. In y direction, it is binned in a log scale. So it is written as 10 power 0, which is 1, then 10 power 1. If I go to larger x, it's going to be 10 squared. So in the y direction, it is increasing exponentially. So in the log scale, it is linear. Okay. So if my function is exponential, then it's good to plot in semi-log scale. Okay. So in plotting log scale, but there's one problem. But I have also negative numbers. Here you can see that for large x, this number is negative, and the log of negative number is a problem, right? I mean, it's not defined. So for that case, we use this Python function or Python command, which says y scale is sim-log, symmetric log. Okay, so symmetric log is if some number is negative, then it takes log of modulus of that object, puts a minus sign. Okay, so this orange line is negative, but I take mod of that and take a log and put a minus sign. Okay, so that's a very useful thing for illustrating functions which are growing with x. Okay, now let's see how to use it to integrate, apply Gauss quadrature. So this function, I mean, it follows from the orthogonal property of these polynomials. I may have it. No, yeah, this is orthogonal property. E to the power minus x, Li, Lj. So these are Ligor polynomials. Dx is delta ij. Okay, is 0 to infinity. So here a is 0 and b is infinity, and the weight factor is e to the power minus x, or weight function. So this is a weight function. Okay, and so we have e to the power minus x fx. Okay, now basically what we have control is this fx. I can put polynomials. I mean, typically it will be some polynomial. So again, the abscissas will be the root of ln fx, and weight wj is coming from here. These are again listed in tables, but following the same special function module of SciPy, you can get them. You can get them printed. Okay, so I want to compute this. Okay, so how many n's do I need for accurate integral? What is n we should use? Number of points. Apply the same logic. So with n points, I can get accuracy up to 2n minus 1. So 4 means 2 times 2 times 2 minus 1. 2 is not enough. I need n equal to 3. Right? So that will go up to 5. Had it been 5 also, with 3 points, it is exact. And it turns out with n equal to 3, I get integral to be 24, which is the exact result. Okay, of course, this can be done mathematically, and there's no problem. But we can also do computationally by Gauss quadrature. We can also work with n equal to 2, but n equal to 2 will not be exact. It won't be 24. Okay.